Good morning. Just picking up where we have left off, and we made the transition from exponential equations to logarithmic equations, and just looking into the first review set, and we have regarding number 14, and I had mentioned that there was a typo error where the 2's here should be subscripts, so those are supposed to be terms in the base 2 logarithm. Okay, so we have in the case of number 14, okay, so we have in the leadoff, okay, so we have the base 2 logarithm of the quantity of x plus 7 minus, okay, the base 2 logarithm of the quantity of x plus 1 is equal to 2, okay, and in terms of sort of sizing things up, okay, again, for logarithmic terms, okay, whatever we have for the attachment should be positive values, okay, so again, okay, we have for x plus 7 and x plus 1 must be positive. All right, and both of the terms, again, are in base 2 logarithms. Okay, so looking at making it to one single logarithmic term, again, we have for subtraction, again, in condensing as a single logarithmic term, okay, we have subtraction is going to imply division. Okay, so we have making it to a single base 2 logarithmic term. Okay, so you have a base 2 logarithm, and anything that stems from positive logarithmic terms, okay, the attachment is going to be in the numerator. Anything that stems from negative logarithmic terms, okay, we're going to have the attachment to be in the denominator. Okay, so we got for x plus 7, okay, so this will go to the top, and we have with x plus 1, again, originating from this negative base 2 logarithmic term, so this will go on the bottom. Okay, and so now we have the base 2 logarithm of the quotient of x plus 7 all over x plus 1 is equal to 2. And again, we wanted to take care of the base 2 logarithmic appearance. Okay, so we have, again, just going back to the property where we have a to the base a logarithm of x equals x. So I can take this property, okay, where I'm going to have the a is going to be at 2. So with both sides of the equation, they will be treated as powers to which the exponential base 2 is going to be raised. Okay, so we have 2 to the base 2 logarithm the quantity of x plus 7 all over x plus 1, okay, is going to be equal to 2 squared. All right, so we have on the left, okay, so we have what's going to be left over, the ratio x plus 7 over x plus 1. And we have it's equal to 2 squared, and again, 2 squared is equal to 4. And looking at setting up what we have in x, so if I take care of the fraction, multiplying both sides, okay, by x plus 1, okay, so we have in following through, okay, so we're going to have x plus 7 is equal to 4x plus 4, and that's after distributing 4 over the sum of x and 1. And so we have like terms on opposite sides of the equation, and so just looking at gathering the x terms and separating from the constants. Okay, so we got for the variable terms, okay, so we got 4x is the higher term, x is the lower, and so I'll just take away the smaller in this case, which will be x, and with the constants, okay, so we have the x terms on the right. So just move the 4 by subtracting. Okay, and so we're going to have 7 minus 4 is 3. And we have 4x minus x becomes 3x. And with division by 3, okay, we're going to have an apparent solution with x equal to 1. And so just looking at what we have to see if the restrictions are satisfied. So 1 plus 7 is 8, that is positive. 1 plus 1 is 2, that is positive. And so we have, on the basis that the algebraic expressions and all and operations are performed correctly, 1 satisfies these restrictions, and so 1 is going to be the solution. All right, and now for what we have in the case of number 16, okay, so we got, in this case we have a single base 4 logarithmic term where we have 2 times the base 4 logarithm of all of x minus 2 is equal to 6. And for what we have in this setup, alright, so I have 2 times, okay, the base 4 logarithm of x minus 2 is equal to 6. Okay. And once again, okay, we have the attachment, okay, to be at x minus 2. And again, just like what I have with x plus 7 and x plus 1, okay, this must also be positive. Okay, and just to start things off, okay, so what I can do here, and one might wonder, okay, if I can perform division since I have even coefficients on both sides. And if you pose that question, well, the answer to that is going to be yes. Okay, so I can make things a little bit simpler. Okay, so looking at what we have with dividing by 2, so this problem becomes a little bit simplified. Okay, where I have the base 4 logarithm of the quantity of x minus 2, okay, is equal to 3. All right, and so we're back in the situation where we have a single logarithmic term set equal to a constant, kind of like what I had in the second step from number 14. So I can re-enter, okay, again, the property where we have a to the base a logarithm of x is equal to x. Okay, so the base a is going to be at 4, and what represents the attachment x is the binomial x minus 2. So I can take care of the base 4 logarithm by treating both sides of the equation, okay, as powers to which 4 will be raised. So just taking what we have, we've got 4 to the base 4 logarithm of the quantity of x minus 2 is equal to 4 raised to the 3rd power. Okay, and so the left hand side becomes x minus 2, and 4 to the 3rd is 64. And so we have, with x minus 2 equal to 64, okay, we're going to have an apparent solution with 66. So with x at 66, if I go back, and we're going to have 66 minus 2 is 64, which will be positive. And so we have our unique solution in x, okay, to be at 66. All right, now looking at what we have in the case of number 17, okay, this time we have 7 is equal to the base 3 logarithm of the quantity of x squared plus 162. Okay, and so we have here okay, so we have with 17, okay, so you have 7 is equal to the base 3 logarithm of x squared plus 162. Yeah, 162. And what I can do here is, okay, And I've been accustomed to having the logarithmic term on the left-hand side of the equation, so I could do like the commutative property of equality switch around, like going from b is equal to a is equal to b. Yeah, so you just refashion this. Okay, so we got the base 3 logarithm of all of x squared plus 162 is equal to 7. And again, just applying the a to the base a log of x is equal to x property, okay, with a at 3. So both sides of the equation, okay, will be powers to which the exponential base 3 will be raised. Okay. So we have 3 to the base 3 logarithm of the quantity of x squared plus 162 is equal to 3 to the 7th. Okay, so for what we have here, left hand side, okay, we have an x squared plus 162, and for 3 to the 7th, now 3 to the 7th is going to be at 2187, and if I take the difference, subtracting 162 from both sides, so we have the x squared is equal to 2025. And just going back to the old square root property of equality. Okay, so we have the square of an expression set equal to a constant, and if I take the expression, we're going to have that by the square root property of equality, okay, we're going to have x equal to plus or minus, okay, the square root of 2025, okay, and 2025 is a perfect square value, and its square root is going to be at 45. So we're going to have a couple of apparent solutions with positive and negative 45. And we have just once again, okay, with any potential restrictions, okay, we had them for x plus 7 and x plus 1 and number 14, for x minus 2, number 16, and then for x squared plus 162, okay, that has also the restriction that whatever we have for x, that this binomial turn out to be a positive numerical value. Okay, so for what we have in this case, right, so negative 45, now the square of the negative is going to be a positive, and a positive plus 162 is going to be positive. So negative 45 fits the bill, and 45 already a positive value, where the square of it, and once we add to 162, also a positive result. So these values are going to check out. So we have two solutions for x in this particular problem, and those being additive inverses of each other. So we have x equal to negative as well as positive 45. Now, for what we have in the case of the next item, and we have for number 18, okay, so we're back to natural logarithms, and we have what's going to be the natural logarithm of the trinomial x squared minus 4x plus 4 is set equal to 0. And for what we have in this one, okay, so you have the natural logarithm of x squared minus 4x plus 4 is equal to 0. And once again, okay, we have with the attachment, okay, it is such that whatever we have for x, that the expression in the attachment again must be positive. Okay, so for what we have now, we got have the natural logarithm, and you don't have to write this out, but you just sort of spell out again, a natural logarithm is going to be a base e logarithm And again, just going back to our property, we have the exponential base to the logarithmic power, okay, that consists of the same base. Okay, we have of x is equal to x. Okay, so we have in this case what represents a is going to be that natural logarithmic exponential base number e. Okay, so we have e to the base e logarithm, or e to the natural logarithm. It's going to be equal to e to the 0. Okay. And so for what we have on the left, okay, we have x squared minus 4x plus 4 is equal to, now we have e, again that's a number that's a little bit higher than 2.718, and a non-zero number to the 0 power is going to be equal to 1. And so we have a quadratic equation, and if I were to take 1 away from both sides, okay, so I'm going to have this quadratic equation to be in standard form. Okay, so we have x squared minus 4x plus 3 is equal to 0. And looking at factoring, so we have with x squared, again this will go to x and x, and factors of 3 that will combine to -4 in terms of adding and subtracting. We have a -1 as well as a -3. And looking at applying, okay, the zero product property, so we have with x minus 1, if that is equal to 0, well, we have a first apparent solution with x at 1, and the next one we have upon applying x minus 3 equal to 0, so we have x is equal to 3, and just checking, plugging 1 in for x, so you have 1 squared is 1, and you have -4 times 1 is -4, so you have 1 minus 4 is -3. -3 plus 4 is going to be positive, and so 1 results as a positive expression. And for 3 squared is 9. -4 times 3 is -12. 9 minus 12 is -3. -3 plus 4 is also at 1. So both of these values with 1 and 3 are going to check out. So again, we have the solution we have to turn out to be 2 distinct values with 1 and 3. All right, now for what we have in the case of number 19, okay, so we got in this equation we had the sum of logarithmic terms, okay, and here we had the base 3 logarithm of x plus the base 3 logarithm of the quantity of x minus 8 is equal to 2. And so for what we have here, okay, so again we have the base 3 logarithm of x, and we have plus the base 3 logarithm, okay, we have of the quantity of x minus 8 is equal to 2. And once again we have for x as well as x minus 8. Okay, so you have x and x minus 8 must be positive. Okay, and now we have going back to starting out with 2 logarithmic terms, and again we have between them is the operation of addition, and looking at combining logarithmic terms that are in the same base into one expression. Again, addition is going to imply multiplication. So for what we have here, okay, we got the attachments at x and x minus 8. So if I consolidate by multiplying the attachments, say the base 3 logarithm of x times the quantity of x minus 8 is equal to 2, and I can just go ahead and multiply the attachments. Okay, so you have x times the quantity of x minus 8, so this will become x squared minus 8x. And again, taking care of the base 3 log, okay, by treating both sides as powers to which, in this case, 3 is going to be raised. And so we have, in this one case, we have, again, not a to the base a logarithm of x is equal to x. All right, so we've got 3 to the base 3 logarithm of the quantity of x squared minus 8x is equal to 3 squared. Okay, so left-hand side, okay, we have x squared minus 8x. And we have this equal to 9. Okay, so we have a quadratic equation. And if I put this into standard form, and we have upon taking 9 away from both sides, so we're going to have x squared minus 8x minus 9 is equal to 0. And just taking what we have now, okay, so I can factor. And we have with the binomials, okay, so you'll have more weight given to the subtraction than to the addition. So we have only x plus 1. And in the case of the subtraction, we'll have x minus 9. And if we have the x plus 1 is equal to 0, okay, we have the x is equal to negative 1. And if x minus 9 is equal to 0, well, we're going to have the x is equal to 9. So we have a couple of apparent solutions. Now going back to the original setup, again, x and x minus 8 must both be positive. And guess what? Okay, with negative 1, guess what? X at negative 1, it fails to meet the requirement that the expressions both be positive. So negative 1, okay, that one strikes out. For 9, okay, you got 9 for x, 9 is positive. 9 minus 8 is 1, also positive. So 9 is going to check out. So for this problem, okay, we have, again, what could have been 2 solutions, but what turned out upon inspection to be only 1 solution. And that solution, again, is going to be at x is equal to 9. Okay, so these are, again, further situations of what we have working with logarithmic terms. Now, and for the second part, okay, in your review handout, again, just going back to logarithmic equations, okay, with 2 and 3 from this second part. Okay, the other day we looked at an exponential equation that had a common base, which then was at 2 in the case of problem 1. Now for what we have in the case of the number 2 in this set, so you have the base 2 logarithm of x plus 1 plus the base 2 logarithm of x plus 3 is equal to 3. Okay. And so we have the base 2 logarithm of x plus 1, again that was plus the base 2 logarithm of x plus 3 is equal to 3. Okay. So again, we're looking at a situation where we have 2 distinct attachments. And once again, both of these must be positive for whatever we have for x. Okay, so now we have the operation of addition between logarithmic terms in the same base. And again, addition is going to imply multiplication. So here we're going to have the base 2 logarithm. We can have multiplying x plus 1 and x plus 3. And I can go ahead and FOIL out the binomials. Okay, so I have the base 2 logarithm. Okay, so this is going to be x squared plus 4x plus 3 you can have equal to 3. And again, just with the a to the base a, logarithm of x is equal to x property. So here, the base a is going to be at 2, and treating both sides here as powers, to which 2 will be raised. Okay, so for what I have on the left, okay, so I have x squared plus 4x plus 3 okay, is equal to 2 to the third, which will be 8. And looking at taking 8 away from both sides, okay, so I'm going to have that x squared plus 4x, and 3 minus 8 is going to be negative 5. Okay, we have is equal to 8. And looking at factoring, okay, so we have the quantity of x plus 5 times that of x minus 1 is equal to 0, and setting the factors each equal to 0. We're going to have the x plus 5 is equal to 0. And so we're going to have the x is equal to negative 5. And for x minus 1 equal to 0, okay, we'll have the x is equal to 1. Okay. And again, both x plus 1 and x plus 3 must be positive. So upon inspecting with x at negative 5, well, negative 5 plus 1 is negative 4. Just the leadoff term fails to have a positive attachment, so we need not even look at the second one because we already have a negative. And with 1 plus 1 is 2, check. 1 plus 3 is 4, check. Okay, so both x plus 1 and x plus 3 are positive at x is equal to 1. And again, we have failure at x equal to negative 5 in terms of meeting, again, these restrictions. So again, we have one solution for x in this equation, and that is going to be with x is equal to 1. All right, now for what we have in the case of number 3, okay, so we got in this one, okay, we have the difference of natural logarithmic terms, and here we have the natural logarithm of the quantity of 2x minus 7 minus the natural logarithm of x is equal to 0. And for what we have in this equation, okay, so I have the natural logarithm of the quantity of 2x minus 7 minus the natural logarithm of x is equal to 0. So let me double check here. Yep, minus the natural logarithm of x. Okay, and so we have for the difference of terms in the same logarithmic base. Okay, once again, subtraction will imply division. So we'll have for the natural logarithm, so we have a ratio, and again, the top part of the attachment will stem from the positive logarithmic terms. And so in this case, we'll have at the top will be 2x minus 7, and on the bottom will be the attachment that stems from the negative logarithmic terms. In this case, we have minus the natural logarithm of x, so x is going to go on the bottom. Okay, so we have this equal to 0, and again, a natural logarithm is going to be a base e logarithm, and we can go ahead and take care of both sides here by treating these as powers to which the natural logarithmic exponential base e is going to be raised. Okay, so we have in the setup, Okay, so you have e to the ln or e to the base e logarithm of 2x minus 7 over x. So this will become 2x minus 7 all over x. And for what we have in the case of e to the 0, okay, so you have e to the 0 is going to be at 1. And just looking at multiplying by x, so you have 2x minus 7 is equal to 1 times x, which will be x. Okay, so just if anyone wonders where this x came from, again, I multiply the equation by x. So I have 2x minus 7 equal to x. And what I can do here is that I can join the x's together upon taking 2x away. And so we have now that negative 7 is equal to x minus 2x, which will be negative x. And then change the sign values from either multiplying or dividing by negative 1. And it's going to turn out that we're going to have an apparent solution with x equal to 7. And once again, okay, we have with the attachments. Okay, whatever we have here for x, in this case it's 7, both 2x minus 7 and x must be positive values. Okay. And so with x at 7, 2 times 7 is 14 minus 7 is 7, that is positive. And you got natural logarithm of x with x at 7, so x is also positive. So 7 is indeed going to check out. Okay, and now for the next group, and just sort of going back, we're looking at, in this case, combining expressions. And we have, in the case of number 9, okay, and we have, for number 9, okay, so you have terms that are in base 5 logarithms. And let's see, for number 9, okay, so you have, looking at combining as a single base 5 logarithmic term. So you're going to have 3 times, okay, the base 5 logarithm of w. And you're going to have minus 2 times the base 5 logarithm of x. Okay, so I have plus 6 times, okay, the base 5 logarithm of the quantity of y minus 4. And we have minus 3 times, okay, the base 5 logarithm of z. Okay, and just looking at combining as a single logarithmic term, okay, where we have the base to be at 5. Okay, and again, when we went in the other direction, where we were expanding logarithms, again, we had converted exponents to coefficients. But in the case of combining logarithmic terms, okay, we'll be doing the reverse. Okay, so going from coefficients to exponents. And so we're going to have in the rewrite pathways. Okay, so first of all, we have the base 5 logarithm of w to the 3rd. Next term, we'll have the negative of the base 5 logarithm of x squared and we'll have plus base 5 logarithm of y minus 4 to the 6th, and we have minus base 5 logarithm of z to the 3rd. Okay, so any leading coefficients that I had, okay, I have converted to exponents. Okay, and so we have among the terms, okay, we have separated by addition and subtraction. Okay, so looking at combining the attachments and thus forming a single base 5 logarithmic term. So for what we have here, okay, so anything stemming from positive logarithmic terms, the attachments will go to the top. Anything from negatives will go on the bottom. So we have, first of all, we have w to the third, so this comes from a positive base 5 logarithmic term. So this will go on the top. And then we have next, we have x squared, which comes from a negative, so the x squared will go on the bottom. Next term we have y minus 4 raised to the 6th. This comes from a positive base 5 logarithmic term, so that attachment will go in the numerator. And then we have a z cubed. Okay, this comes from the last base 5 logarithmic term, which was subtracted. So the z to the third is going to go on the bottom. And so this will be the final form upon which we can express the consolidated base 5 logarithmic term. So what we have in w and y will go in the numerator, whereas what we have for x and z will go in the denominator. Now, in the case of what we have regarding, okay, number 10, okay, and we have with this item, okay, we have one radical expression in the mix. And I'll just go ahead and rewrite this one. Okay, so we have for number 10. Okay, so just kind of reintroduce this problem. So still have 2 times, okay, the base 3 logarithm of u, and have plus 3 times the base 3 logarithm of the quantity v minus 4 minus 3 times, okay, the base 3 logarithm. And what's going to happen here is that for the square root of w to the 4th minus x cubed, okay, we've got w to the 4th minus x cubed. Now the square root of this will be this difference raised to the 1/2 power. Okay. And looking at establishing the follow-through, okay, that we have in the mix. Okay, so we've got in this arrangement. Okay, so we have again, just looking at converting from coefficients to exponents. Okay, so we have the base 3 logarithm. Okay, what is going to be u to the 2nd. And we have plus the base 3 logarithm of the quantity. Okay, we have v minus 4. It's going to be to the 3rd power. And then we have minus. Okay, and that 3 is going to be in its own capacity part of the formation of the power to which w to the 4th minus x cubed quantity is going to be raised. So you have minus, okay, the base 3 logarithm. Again, just kind of adding parentheses to create a layer upon which the 3 is going to affect what is already the 1/2 degree. Okay, so we have the base 3 logarithm. We're going to have w to the 4th minus x cubed. Again, we have already to the 1/2, and with the 3 converted in exponential capacity, okay, this expression is furthermore going to be raised to the 3rd power. So we have for now, okay, we have the base 3 logarithm of u squared. So for just this individual term, in terms of what needs to be done, okay, that's already taken care of, and also for v minus 4 to the 3rd, okay, we have things taken care of with that one prior to the condensing into one term. But with the work that remains prior to making into a single base 3 logarithmic term, I still have this exponential work for w to the 4th minus x cubed that remains. And so in the follow through, we have with the power property of exponents, we have a base to a power to another power is going to be that base to the product of those powers. And in this case, we have w to the 4th minus x cubed, which will be raised to the 3/2 degree. Okay. And now, so I have all the coefficients taken care of and the exponents finalized, and then creating again a single base 3 logarithmic term with what we have in the expressions we have in u, v, w, and x. Okay, so you got u squared comes from a positive base 3 logarithmic term, so this will go in the numerator. And for v minus 4 to the third, this comes from a positive base 3 logarithmic term, so its attachment goes also in the numerator. And for the difference of w to the 4th minus x cubed to the 3/2, this comes from a negative base 3 logarithmic term, and this attachment will go in the denominator. Okay. So w to the 4th minus x cubed to the 3/2. Okay, will go on the bottom. And if there were any other way to write this, you would have like the base 3 logarithm of u squared times the quantity v minus 4 to the third, and from w to the 4th minus x cubed to the 3/2. This would be like if I were to express in radical terms. So the 2 dictates the type of radical there is. In this case, we'll have a square root, and it'll be the square root of w to the 4th minus x cubed quantity to the 3rd power. But again, the version with the non-x integer exponent, that will suffice. All right, now looking at what we have still from the page, and we have going back to what we have with compound interest, and we'll look into systems of equations like what 14 and 15 will be referencing. And we have in the case of compound interest, okay, and we have in this one, so for 16, and also in the case of 17. Okay, so in both of these problems now we have the principal is going to be at $3,000. And we got 6%. And the time span in both situations, okay, we have for 6 years. Okay, and 16 you're looking at quarterly compounding, and for 17 you're looking at continuous compounding. Okay, so just creating a bit of a backdrop. Okay, for number 16, okay, we have you can see have quarterly compounding. And for the non-continuous future value formula, again, so we have A is equal to P times the quantity. Okay, so we have 1 plus R over N to the N times T power. Okay, and just filling in the values. Okay, so we have upon substituting, so we have for P, we've got $3,000. We have times the quantity for 1 plus R over N, so R is at 0.06. And N, we have it 4 with the quarterly compounding. And for the N times T degree, okay, so you have 4 times 6. Okay, so you have the 24th power And so we have in terms of following through. Okay, so you got $3,000. And 0.06 over 4 added to 1, so that's going to be 1.015. Then we have to the 24th power. And for the number here, okay, so we have a decimal. And for what we have in the case of 1.015 to the 24th, and we have among the first digits, you have like 1.4295. And multiplying by $3,000 and putting in terms of dollars and cents. Okay, so we have about 4,288.51. And again, that's after 6 years of quarterly compounding. Okay, and again, with the same basis, with the principal, the rates, and the time. Okay, the more frequently the compounding is done, the higher the balance is going to be. And once again, for the theoretical maximum, okay, this is going to come from continuous compounding, where this statement is transformed to a is equal to p times the natural logarithmic base e raised to the r times t power. So we have, filling in, okay, so we have p, we have a $3,000. And for e to the rt, so you have e to the 0.06, t we have at 6. And here we have $3,000. Okay, we have times e to the 0.36. Okay, and so again, we have with that e value, again, that number we have right at 2.718, and for e to the 0.36, we have $3,000, and this number we have like 1.4 33329 and some places after that, and multiplying by $3,000 and putting this in terms of dollars and cents. Okay, we are very close to $4,300, and rounding to the nearest penny, okay, we end up right at $4,299.99. Okay, so this is what we're going to have again with continuous compounding, and this is going to be theoretically the maximum attainable result with $3,000 at 6% compounded for 6 years. All right, now again, just touching upon annuities, and we have Rory, okay, who is looking at retiring in 15 years. Okay, it says he contributes $1,000 to an IRA on a quarterly basis, and it's asking what would the value of the IRA be when Rory retires if the rate of return is assumed to be 10% compounded quarterly, and Ray invests, or Rory, yeah, Rory Ray's his name, or Ray Rory, anyway, invests at the end of each quarter. Okay, so we got in this one. Okay, so we have with the annuity situation. Okay, and again, just for the traditional annuity formula, okay, that's the one that's on the conservative side. Okay, we have, again, so you have a is equal to p times the quantity of 1 plus r over n raised to the n times t minus 1 and we have times n over r. Okay, so for what we have in the case of the building blocks here. Okay, so we have P is equal to $1,000. And again, just sort of stress in case they have at the end of each quarter. And for R, okay, so R is at 10%. And in the numerical calculation case, so R is going to be at 0.10 or 0.1, okay, and we have just like the frequency of the deposits, okay, the compounding is done quarterly, so N is equal to 4. Okay. I think the time span was for 15 years. Okay. Okay, so just taking what we have with the annuity formula. And again, this is the theoretical minimum, and this is the one that's like in terms of everyday investments, that sort of stuff, where annuities are configured. This is the formula, or at least a little variation of it, that is typically used. And now, for what we have with P, okay, so we're looking at $1,000. Times the quantity and filling in. Okay, so we have 1 plus. Then we have with R over N. Okay, so we have 0.1 divided by 4. And for N times T, okay, so this is going to be 4 times 15. Got minus 1, you have times N over R. So N we have at 4, R we have at 0.1. Okay, so for what we have in the setup, okay, so you got for the sum, okay, have 1.025. Then we have to the 60th. And we have minus 1, and 4 divided by 0.10. Okay, so that's going to be at 40. And for 1.025, okay, to the 60th. Okay, and we have for that figure, okay, so we have 4.3997 among the first digits. In other words, very close to 4.4. Okay, just with the difference. Okay, so we have $1,000. We have times 3.399789. 7. See, if I keep this and multiply by 1,000, the principal as well as the N over R, which is 40, and we have for the value in 15 years, okay, we have right at $135,000. $991.59. Okay. And again, just for what we have for the other portion, okay, if Rory happened to, undergo the activity of $1,000 in recurring deposits at the beginning of each quarter as opposed to the end. Okay, so this is going to be your theoretically maximum balance for this IRA. Okay, so again, you have just about all of the same ingredients, okay, and just one small but yet key detail. And again, that's just going to be the 1 plus R over N factor. Yeah, so you got the annuity formula times 1 plus R over N. Just that key element, okay, is the difference. And for, again, what we have for 1 plus R over N, and we dealt with this moments ago in the annuity formula when working with the numbers inside the brackets. So just sort of repeating, and we have with 1 plus R over N. Okay, so you have 1 plus 1/10 divided by 4. So you have 1.025. Okay, so it's going to, so between the maximum and the minimum, you have that 2.5% difference. Okay, so again, we had with the minimum, okay, where Rory was investing at the end of each quarter, okay, we had this future value, and for the maximum, we're looking at 1.025 times that. Okay. So looking at what we have in terms of the numbers here, so multiplying by 1.025, and we have in terms of dollars and cents. Okay, so we're looking right at $139,391.38. Okay, so you're looking at a difference of almost, so it looks like $3,400 after 15 years. Okay, so you have 139,391.38 as the end result. Okay, now just looking into what we have in the next go round, and this is going to be for what we have in the case of systems of equations, and there will be at least a couple of types we will be dealing with, and let me give you a bit of an intro. Okay, so for what we have in the case of systems of linear equations, okay, and we have just for the general setup here, and we'll look into two equation systems, and we can say we have a of 1x plus b of 1y is equal to c of 1. And we have a of 2x plus b of 2y is equal to c of 2 and we have for the system above for the system above, okay, if there is one solution if there's one solution, the graphs will intersect at the point xy. And give you just an example of a system. Okay, so if I'm looking at solving for x and y, let's say we have first of all, let's say that we have 3x minus y is equal to 3. And we'll say that we have simultaneously, okay, that x plus y is equal to 5. Okay, and in terms of solving for x and y, so this is our system, and what we can do, okay, if you notice we have we've got 3x and x, and we've got negative y, and we've got 3 and 5, to which the first and second equations are set equal respectively. And one approach, if you notice we have already additive inverses with negative and positive y. So what I can do here as one approach is add the equations. Okay, so 3x minus y is equal to 3, and x plus y is equal to 5. And if I add together, okay, once again, the negative and the positive y will cancel out. Notice we got 3x plus x is 4x, and 4x is equal to 8. And with division by 4, okay, so we have at least x. We're going to have, okay, and x is equal to 2. So I got x now for y. What I can do is I can use either of these two equations. So I can just plug in 2 for x in either equation. It can be either of these two, and just like it might be a little bit quicker to go with that x plus y is equal to 5. So we're going to have here, got 2 plus y is equal to 5. And with y, okay, it'll be 5 minus 2, which is going to be at 3. Okay. And so just looking at what we have here, you can double check. Okay, with x at 2 and y at 3, 2 plus 3 is equal to 5. And 3 times 2 is 6. And 6 minus 3 is equal to 3. And so what's going to transpire, okay, is that for the solution, okay, so you have x is equal to 2, y is equal to 3. And another way you could write this, I know that Alex can sometimes be big on the ordered pairs. In this case, we have xy is equal to 2, 3. Okay. So this is a sample of a linear system, okay, and this one we could pretty much get to the solution right away, since I had automatically additive inverses with negative and positive y. Now let's say that if you have a system that's going to have at least a solution, and where the mode of solving is maybe a little bit less automatic. And what I mean by this, okay, is that if I have, let's say for instance, x plus 3y is equal to 5. And I have 3x minus 2y is equal to negative 18. Okay, so we have for this system, notice before I had additive inverses with negative and positive y, adding the equations, so I have x left over to solve for and get to first. Whereas here I don't have the automatic elimination. But what I can do here is I can create a strategy, okay, where it is to eliminate one variable and solve for the other. And this can be done by adjusting one equation or both equations. What do I mean by this? In other words, adjust one, if not both equations, where I'm going to have at least a set of additive inverse terms in either x or y, where I can provide elimination. And see, if I have like x plus 3y is equal to 5, and I got 3x minus 2y is equal to negative 18. Now one approach can be, well, I got x and 3x. I got 3y and negative 2y. And something that might come to you first is that looking at x and 3x, like what's going to eliminate 3x? It is not going to be x, but it's going to be a negative term. So the additive inverse of 3x is going to be negative 3x. So what I can do here, what I mean by adjusting, I can adjust the first equation, and to keep everything aligned or in proportion, I can just take negative 3 times the first equation. So we have negative 3x plus 9y, we'll make that negative 3x minus 9y. So negative 3 over x, we have negative 3x, negative 3 over 3y, that's going to be a negative 9y. Negative 3 over 5 becomes negative 15. And I can just duplicate the second equation. So I got 3x minus 2y is equal to negative 18. And upon adjusting, okay, so I can add the equations together. Okay. So we have negative 3x, and 3x will go out. And we have negative 9y plus negative 2y is going to be negative 11y. Negative 15 plus negative 18 is going to be negative 33. And so we're going to have our solution for y is going to be at 3. And again, you can plug in for y in any of these equations, even the multiple. So you can have your choice. And looking at what we have now, let's say we have plug in 3 for y. I'll just go with this equation. It'll work for any of them. Again, so I had x plus 3 times y is equal to 5. And plugging in 3 for y. So we have x plus 3 times 3 is 5. So we have x plus 9 is equal to 5. And so we're going to have that x is equal to -4. Okay, and you can go back and check. So we have with x at -4 and y at 3. Okay, so 3 times 3 is 9. We've got -4 for x. -4 plus 9 is equal to 5. And we have 3 times -4 is -12. -2 times 3 is -6. And -12 minus 6 comes out to -18. Okay, so this will have one solution. And this will be with x equal to -4. And y equal to 3. And so putting in ordered pair terms, okay, we have the point or the location at -4, 3. And just kind of a brief mention, and we have in the crossover to looking at what we have concerning systems of nonlinear equations. And for systems of nonlinear equations, what that means is that we have like either x or y or both to be expressed as variables that are no longer raised to the first power. And we'll say that if I'm looking at solving for x and y, okay, now we'll say that for this system, if I have simultaneously that x squared plus y squared is equal to 61, and also at the same token for the same set of values x and y, not only will I have the sum of the squares be at 61, but I can arrange it where the difference of the same squares will be at 11. Okay, so I have x squared plus y squared is equal to 61, and also where x squared minus y squared is equal to 11. If you notice, I already have additive inverses with positive and negative y squared, and for what we have in this particular case, so looking at combining, so I have x squared plus y squared is equal to 61, and x squared minus y squared is equal to 11. Okay, so if I add together, so we have positive and negative y squared to go out. So right now we've got 2x squared is equal to 72. And we have with division by 2. Okay, so I have 2x squared over 2 is equal to 72 over 2. So this will come down to x squared is equal to 36 So I got a quadratic equation, and you can either take the square root property of equality, or you could take this equation and write x squared minus 36 equal to 0 and factor. You have your choice. I'll just go with the square root property of equality. So I'm going to have that x is equal to plus or minus, okay, the square root of 36, and we'll have that x is equal to positive or negative 6. And in terms of solving for y, notice that both of these equations are in square terms. So what I'll do here, I can take either the first or the second equation, and I'll go with the first one. And by this, okay, so I'm going to plug in 36 plug in 36 for all of x squared, and so we have 36 plus y squared is equal to 61. And now if I take the difference between 61 and 36, I'm going to have that y squared is equal to 25. Now from this, okay, if I go with the square root property of equality, so y is going to be plus or minus the square root of 25. And so y is going to be plus or minus 5. So for what we're going to have in the, at least in terms of the big picture, okay, you have not one solution point but multiple solution points. And we have, in the case of the solution, okay, so you have x equal to plus or minus 6, y equal to plus or minus 5. And the way you can write this, okay, is that we're going to have 4 points, and among these, say when x is positive, say y is going to be 5 or negative 5. And if I map with x at negative 6, our corresponding points will be negative 6, positive 5 for y, and also negative 6 for x, and where y is at negative 5. So all 4 of these combinations for x and y will satisfy these two equations in the system, where we have x squared plus y squared equal to 61, and x squared minus y squared is equal to 11.